Good evening, Internet. I am Matt Buyak, and this is my second video about calculating prime factorizations using C and C++. So in the last video, we wrote a class for calculating prime factorizations using perhaps the dumbest possible algorithm. That is, we would just start by trying to divide by 2, divide by 3, divide by 4, etc., until we found all of our prime divisors. Basically just brute force. But it turns out that often that's good enough. If we're just factoring a single number, a small number of integers, integers that aren't very large, then that's a perfectly acceptable approach. And in fact, in order to do much better than that, for factoring just a single integer, you have to use much more sophisticated mathematics. Probably beyond the scope of this video and frankly beyond my own mathematical capabilities. That said, usually we're not just factoring a single integer. For example, problem number 21, which you'll see here, was sort of the problem that led to me starting this series on prime factorization. That problem asked us to factor all the numbers up to 100,000. And so if we're factoring many numbers in a range, then it turns out there actually is a much better algorithm. We can get some assistance from our primes class that we wrote a while back. Now I did a whole series on prime numbers and calculating prime numbers. So I'd recommend you check that out. But basically, we just used the classic algorithm, the Sieve of Eratosthenes, to determine whether numbers are prime or not. Basically, building up this array of Boolean values where each bool indicates whether the corresponding integer is prime or not. But instead of just storing Boolean values, we could actually store something more useful. And in particular, with just a slight modification, we can change our algorithm to store the largest prime divisor of each number, which basically lets us factor any number in that range very quickly. Now, it should be noted that calculating primes is also very expensive, but we only have to do it once. Once we've calculated all the primes in our desired range, then we can quickly factor any number in that range. So with that opening complete, let's get to it. So we'll start by opening up our factors class that we wrote last time, which you'll see here. And so what we're going to do is just add a method to our class, also called factor, but it will take an instance of the primes class to assist us in our factorization. And then if we switch over to our primes class, yes, you'll see here that we currently have our sieve with each integer mapping to a Boolean value, and we're going to replace that with a uint32t. Now, this has the unfortunate side effect of significantly increasing our space requirements. But modern computers have gigabytes and gigabytes of memory, and so that's probably not going to be a limiting factor. If it ever does happen to be the case that we need to have a more efficient primes implementation, I have some ideas on how we might make multiple templated versions of the primes class, but that's for another video. Okay, so now let's add here our largest prime divisor. And let's rename our member here. It's now not indicating whether a number is composite. It's just a lookup table for the largest prime divisor. So we'll just call that LPD. Okay, so here's the implementation for our primes class. We'll have to go through and look at everywhere that we were using composite and update it for the new usage. So this is going to be the same. Now, checking whether a number is prime, you'll notice that if a number is prime, then its largest prime divisor will be itself. And so we'll just say, return LPD is equal to n. But we have to be a little bit careful because if we think about what we're going to put in LPD for the numbers 0 and 1, there isn't really anything that would make sense. For example, if we were to set the largest prime divisor to of say 1 to anything that's actually a prime, well, that would be indicating that it's divisible by some prime, which it's not. But if you set it equal to 1, then it's kind of suggesting that 1 is a prime, which it's not. And so really we should leave those just undefined and not use those values. And so we should say return n is greater than 1 and LPD of n equals 1. So if n is equal to 0 or 1, then we'll just return false. Okay, now we can add our new function. Largest prime divisor. And you'll note that with these methods, before accessing LPD, we check to make sure that it's large enough. So we'll need to do the same here. So we'll say while LPD.size less than or equal to n, expand Sieve. Okay, and then we can just say return LPD of n. And we'll probably want, just to be safe, we'll add assert.h. And then we'll say assert n is greater than 1. Okay, so continuing on. So you can see before we were explicitly setting 0 and 1 to be composite. As I mentioned, they're kind of a special case. I'm going to change how we actually handle that just by saying if start is less than 2, then we'll say start equals 2. So this is not even defining those elements, because really there's nothing we can put in there that would make any sense. And so we should just avoid touching those altogether. Okay, continuing on here, we have, this will be LPD.size. And now we get to the first place that we're actually going to be writing to our sieve. And you can see now why I suggested that we can update this algorithm to store the largest prime divisor, because we already have it right here. This prime P is going to be the largest prime divisor for J at the given point in time. And we might update that value multiple times as we find more primes, but by the time the algorithm completes, it will be the largest prime divisor. And so we can just say LPD of J is equal to P, like that. Okay. Again, LPD.size. All right, so when we get to, going back to the way our underlying data structure works, we store LPD in a vector, and when we resize it, the uninitialized values are going to be 0. And so if we get to a given value and LPD is equal to 0, then we know that it's prime. So we'll say if not LPD, that is if it's still 0, then we'll want to say LPD of I equals I, and then add it to our primes here. Then we continue to write the multiples of that prime to all the slots greater than that prime, and so we will say, just as above, LPD of J is equal to I. All right. Oh, and we will need to update this as well. I keep mistyping that. There we go. Okay. So the reason I'm not just doing a find replace here is I want to actually take a moment to consider each place we were using that composite and make sure that there isn't any more isn't any change to the logic that needs to be made. Okay, so I think that should be good. Let me go back to our factors.h for a moment. Since we haven't actually implemented this, I want to make sure that we our update to primes was successful. Yes, okay. This is the wonder of having testing. We can just go and check and make sure that it's still working. Great. Okay, so now we've updated our primes class so that we can get the largest prime divisor of a number. And so now we can add our new factor implementation to our factor class. Okay, so as before, we'll want to have this PP structure here, prime power. We'll find that to be useful. And so let's just say while n is greater than 1, we'll say pp dot prime is equal to p largest prime divisor of n, and pp dot exp equals 1. Okay, and n divided by equals 1, or not 1, excuse me, pp dot prime. Okay, and then we'll say while n is greater than 1 again. And p largest prime divisor is still n. You'll note we need to be a little bit careful here because we don't want to call this largest prime divisor with n is equal to 1. As I mentioned, that's going to hit our assertion that we wrote earlier. And so that's why we're checking to make sure that n isn't 1 before we call this. Okay, so oh, excuse me, we want this to be pp dot prime is equal to that. Okay. While it's the same divisor, we'll say plus plus pp dot exp and n divided by equal pp dot prime. Okay, so now we should have divided out all multiples of that prime from our value n. And so now we can say factors dot push back pp. Now you'll notice that this is assembling our prime factorization in the reverse order from our implementation up here. This implementation will have the smallest divisors first and the larger divisors last, and this will be the opposite order. And at this point, it doesn't really matter. We haven't specifically defined it to be one way or another. But we should probably be consistent because there might be algorithms that we implement at some point in the future that rely on it being in a particular order. And in general, there's a theorem, the fundamental theorem of arithmetic, which states that the prime factorization exists and is unique. And if we allow it to be ordered either way, then it isn't actually unique. And so let's make sure that it's ordered correctly. We'll just say std reverse, and we'll say factors dot begin, factors dot end. So this is just gonna swap the order of that vector. And I've pulled up the documentation for that here. You can find this at cppreference.com. Reference for all things C++. And so that will guarantee that our factorization is in order from smallest factors to largest factors. Okay, so that should be good. Let's see if that does indeed compile. It does not. Let's see what, looks like I did not include primes.h. Okay. It says that factors was not declared. Yeah, I didn't actually put this in our class. And we'll need to include algorithm. Okay. All right, so in the last video, we wrote a test or set of tests for our factor for our factorization class here. And so we can just easily change this test to use our new implementation. It's as simple as that. And so now we can check to see if our new implementation is working correctly. So let's go over to our tests. Oops. All right. Oh, so this is something I haven't been very good about with my header files. In theory, I should be doing pragma once. So this prevents the header file from being included multiple times. And so, yeah, this will fix our error here. Okay. Nope, we want factors tests. Okay, so it looks like, let's see, factorization has value 1, expected 1. Well, that's very curious because that sounds like it passed. All right, let me see what we're doing that makes it unhappy here. We want to be careful because factor. Oh, I see here. I wasn't actually calling or setting n equals to n and doing factors dot clear. Okay, there we go. Our test is passing. Again, the magic of having tests. We can make sure that we didn't break anything. Okay, so we've got our new implementation up and running. Before I call the end to this video, I want to do a little bit of performance testing, and just to show you, what the advantages are to our new approach here. So let's, we don't need to do the primality testing here. And then this will be executed in either case, so and it's pretty cheap, so we'll just leave that there. But let's switch back to our old implementation for a moment and crank this up to 250,000. So this is, again, using our implementation from last time, and we're just going to see how long that takes to run. So we'll do time, and we'll give that a little bit. Hopefully it won't take too long. There's an important balance between making my point and there we go, okay, and taking too long to finish. It was 16 seconds. Okay, so that's not too bad. So let's try now switching back to our primes-based implementation. So we'll say time factors test. Boom, done almost immediately. Yeah, so you'll see that that's something like 200 times faster, I think, something on that order of magnitude. So in this case, when we're factoring a bunch of primes all in the same range, you can see that this approach is much, much better than what we were doing before. It's always very satisfying to see your work, have such a dramatic impact like that. Okay, so you might wonder, like, why then? Why are we keeping this one around at all, the old implementation? And so, like I was saying in the introduction, there are cases where this is actually the approach that you want. For example, let's actually. Let's do this. So let's suppose we're only factoring a single integer rather than a full range of integers here. And so we'll say I is equal to, let's see, and I've prepared a sample input. Let's say 293 times 307 times 311. This is just 3 prime numbers all around 300. So their product is roughly 27 million, something in that range. Okay, so let's see, again, this is our primes-based implementation that we're using here. So let's see how this does. Just factoring one number. just one number. And there we go. Okay, so 12.5 seconds or thereabouts. Now, as before, we'll switch back to as I described it, the dumbest possible implementation. Boom, done basically instantly. So this shows how using different implementations in different circumstances can really get you some significant performance gains. But you have to be aware of how the different algorithms work and what their different advantages and disadvantages are. Okay, so that will be the end of this video. In the next video, we're going to go on to problem number 22.